as you know, we professors live through our students. They do the work. We are just the conductors. So the presentation will be by two my most recent and last, unfortunately, last PhD students, Carolyne Matl and Isabella Wang. What they will present is something that I believe it's not today in industry, but it's going to be in next 5 to 10 years, which is how to deal with robotic interaction of materials that are continuously mechanics. Our mechanical engineers gave us tools for last 100 years, or maybe 50, on continuous mechanics, which is how different soft materials change shapes and deform, and how can you manipulate such materials, like think about in a bakery. You have a dough and you need to manipulate this dough in some more predictable fashion. So in order to have the predictable model, you really have to have the understanding of the viscosity and deformability. I will not talk more, and then Isabella will talk to you about how, again, our mechanical engineers provide us all this finite element analysis. Okay, but in reality, when you need to interact in real time, computationally feasible, you have to simplify. And you have to simplify from moment to moment to change the possible simplification of manipulability. So that's what Isabella is going to talk, and I will stop here. And Carolyne, the floor is yours, and then I don't think I have to introduce Isabella separately. So here you go.
Thank you, Růžena. All right. Did I just turn it off? Can you guys hear me? Okay, cool. So, hi everyone. As Růžena said, my name is Carolyne Matl. I am a research scientist at Toyota Research Institute, where right now I work on mobile manipulation. Prior to joining TRI, I was at UC Berkeley, where I graduated last year, and for my dissertation with Růžena, I focused on the robotic manipulation of complex materials like liquids, grains, and doughs. So I have to honestly say my background is from robotics, and I don't know much about manufacturing, but I've learned a lot about the field in the last few days or so. So I have to say it's nice to get some perspective. So thank you all the presenters and the organizers for this opportunity. Now, in the field of manufacturing, a decent portion of what we traditionally think of as raw materials comes in the form of liquids or grains, for instance, in biopharmaceuticals. However, as the food manufacturing industry is continuing to grow, another category that I think is interesting to think about is dough manipulation. Dough-based foods are quite essential across all cultures. We have all types of breads like pizza dough, dumpling dough, and from this side of the world, knedliki. But if any of you have tried, yes? It is. Oh, I haven't changed the slides. Thanks. But if any of you have tried manipulating dough, it's probably some of the most difficult material to handle. So even for humans. So you can imagine how difficult it might be for a robot to handle this type of material. So today I want to present my last two works I published with Růžena last year that try to tackle this challenge of manipulating dough, or what we call deformable elasto-plastic objects, and we do this by using our custom, very simple, soft tactile hand. Okay, so what makes manipulating dough so difficult? I can think of several reasons why, but the first things that come to mind are that they can be everywhere from crumbly and dry to wet and sticky. And these material properties are basically exist at opposite ends of the spectrum, and they require different techniques for manipulation, as you can see from these expert human demonstrations. Dough also has time-varying properties. So you can start off with a sticky and malleable dough, and then end up with a dry and stiff dough. So in our work, we haven't tried to tackle these conditions yet, but I'm just putting this out there to maybe inspire some of you to begin thinking about ways to deal with these adversarial conditions. So the dough that we manipulated in our work lies somewhere in between those prior examples. We used Play-Doh, which is not sticky and is not crumbly when hydrated properly. Even then, we have to deal with the fact that this material, okay, it's working. Okay, so basically the dough that we're trying to manipulate in our work is elastoplastic. So it exhibits both plastic and elastic properties, hence why we refer to it as deformable elastoplastic, as a deformable elastoplastic object. Okay, so what does that mean? When you press into dough, some of this dough springs back, but there's also some permanent deformation that can result from this forceful interaction. So note that we're already technically simplifying this representation by considering it as elastoplastic, which is rate independent of the applied loading force, instead of viscoelastic, which is rate dependent. Luckily, the way in which we have our robot interact with the dough, time is a less crucial variable, so this elastoplastic representation works perfectly for us. Okay, so given the characteristics of soft deformable material like dough, which has these regions of elasticity and plasticity, we wanted to come up with a way to interact with the material delicately to enable both the perception of the geometry and the stiffness of the material without creating any unwanted permanent deformation. So that would be perceiving within the elastic region. But additionally, we wanted to enable intentional deformations of the material through interactions with sufficient load force. So this would be intentionally acting within the plastic region of the material. And ideally, we'd like to also optimize how we interact with and manipulate these materials, and we want to explore this idea within the context of shape servoing. So this talk will address these challenge criteria in two parts. So in the first, we'll discuss how we designed a variable stiffness soft tactile hand that was used for both sensing and actuation to impose load forces on deformable objects. And in the second half, we'll examine how we can use this new technology to efficiently shape servo dough with model-based reinforcement learning. Okay. So the first set of criteria ultimately led us to design a hand made of soft compliant material, which the robot could vary its stiffness via a simple actuation mechanism. And we called this hand Stretch, or soft to resistive elastic tactile hand. Stretch is a low-cost robotic hand attachment that you can make very easily in your own living room. At least that's what I did during the COVID-19 shutdowns. And you can see that it's composed of a flat elastic membrane that can be cast very easily by pouring EcoFlex silicone into a rectangular mold. And we attach this membrane to a parallel draw gripper using Velcro. And as the gripper increases its gripper width, the membrane's internal strain increases, and this subsequently increases the stiffness of the membrane. So this allows us to vary the stiffness of the membrane to impose different load forces on the environment. Now, because we designed Stretch to be so compliant, by imaging the membrane while it's in contact with the environment, we can use it at its low stiffness regime to reconstruct the geometry of very deformable objects like paper boxes or 2D wire shapes like this circle through simply just touch. And in addition to estimating the contact geometry, we also wanted to estimate the contact load imposed by the membrane onto the object. Now, because Stretch can vary its mechanical response, we can estimate the stiffness of deformable objects via active palpation. So this graph here shows multiple indentation depth to load force curves that correspond to different stretch states of the membrane, where higher curves correspond to the membrane being stretched more. One more, okay. Now, ultimately, we want to find the force at which the object finally deforms. If we imagine this object to be an elastic body with 1 degree of freedom, we can divide the estimated load force by the amount of deflection the object experiences to make an estimate of the simple proxy for stiffness in newtons over millimeters. We can use this force depth profile on the right to save time and efficiently modulate the stiffness of the membrane so that the load force increases monotonically with each new contact condition. So that's the active palpation part. Now, we use this technique with the robot to measure the stiffness of 4 balloons filled with different materials, ranging from air, water, chia seed pudding, which is this mixture of water and chia seeds, and dried chia seeds. And even though these are technically proxy values for stiffness, since we're using this simple 1 degree of freedom model for stiffness, you can see that the values still increase with each object, as we would expect, and the estimated values are sufficient for differentiating between materials within this range. Also note that we'll be reusing this proxy for stiffness in our dough rolling work, where this estimate actually enables more efficient rolling. Okay, so here we're just wanting to show that we can use this elastic hand design to roll blocks of Play-Doh into balls of dough. The robot is able to track the position of the dough while maintaining its contact with the dough, which is something that would be quite difficult to actually do with a traditional rigid end effector. Okay, so this second half of the talk, we'll talk about how we used model-based reinforcement learning along with a similar soft tactile hand made completely of elastic bands this time to accelerate the task of rolling out a ball of dough into a breadstick of a specific length. So first note that this task of dough rolling requires dynamic interaction of a deformable end effector with a deformable object. So this involves highly complex and high-dimensional dynamics that are difficult to model even today. So instead of explicitly representing the dough-to-hand interactions, we used model-based reinforcement learning to learn a transition function for these interactions. So what this means is we learn from data the relationship of given an action applied to the dough and its current state, what will the dough state be after that action is applied? So we model this, this model is represented here by F. Now within this framework, we use model predictive control to select the best action to take at this time step given the current state of the dough. This is done by optimizing the cumulative expected reward over a certain number of time steps into the future. So we're looking ahead where at each time step, reward is calculated as simply, in this case, how close is the dough to the desired goal shape. And what the reinforcement learning framework adds to model predictive control is that it allows us to iteratively update or improve the transition function F to better reflect the dynamics of the dough and hand interactions. This also means that if we start off with the wrong model or a poorly initialized model, then the algorithm still has time to self-correct. So earlier I said this interaction is highly complex, but so in order to keep the optimization problem tractable, we helped ourselves out by simplifying the state and action space. So by modeling the state as simply the bounding box of the dough formation, that was sufficient for our objective to track the dough's state over time. As for the action space, we limited the variable parameters to the stiffness of the hand's elastic membrane, which we can vary by stretching or closing the gripper, as well as the depth at which the robot pressed the dough. These two parameters were chosen because they directly affect the load force imposed by the elastic hand. Now, the rest of the robotic action was fixed in that each roll consisted of a back and forth motion at the highest point of the dough formation, and this was for every action applied. Now, given all these simplifications and action constraints, we were able to train a dynamics model of these interactions with only about 1 hour of robot time, where the robot was randomly interacting with a ball of dough under these specific action constraints. And so we can see here that comparing the reinforcement learning methods on the right with a random and heuristic policy, all of which were under the same state and action simplifications and constraints, the robot was able to roll the dough out into the 6-inch log with significantly fewer rolls. Also, the robot was able to efficiently roll the dough into different length breadsticks using the reinforcement learning method along with the cross-entropy method for optimization. However, what happens if the dough that is being manipulated now has different material properties than the one that was used for training? So this could mean that it could be drier, which could cause it to be less malleable and stiffer, or it could be well rested, which means that it's very easy to plastically deform. Well, because this model-based RL framework allows the robot to iteratively improve the dynamics model given new observations as the robot in real time interacts with the dough, we show here that it's able to still self-correct and efficiently roll out a stiffer dough much faster than compared to when using a fixed model with just model predictive control. We also showed that you can use stretch to estimate a proxy for the stiffness of the doughs in order to calibrate the model quickly so we can more efficiently roll the dough out. So here we're showing that we were able to demonstrate through our experiments that these stiffness measurements do indeed help the robot regress to a better dynamics model for the dough interactions, which led to significantly more efficient rollouts. Okay, so as a brief recap, through these two works, we explored how we could use a very simple variable stiffness soft tactile hand to sense the contact geometry of very soft deformable objects, as well as to measure a proxy for stiffness for deformable objects, and to finally to use that technology to efficiently shape servo dough. I'd like to say, however, that there are several avenues of future work to explore. Since we really view this work as a stepping stone into new directions, perhaps using soft robotic manipulation with materials like dough. Okay, so in terms of future work, one direction, for instance, is, well, while our simple state and action space of the dough allowed us to simplify the dimension of our problem, therefore letting us our optimization problem be more tractable, a higher dimensional space would certainly allow us to explore more interesting shape servoing problems, as well as to allow us to create a tighter sensory action loop. So furthermore, there's a lot of great recent work on modeling deformable contact and deformable objects, some of which you will hear about in a second from Isabella. And I think we're getting close to being able to use some of those techniques in the application of dough manipulation. And finally, because this work was done during COVID times, Play-Doh made the experiments a lot more manageable to do in a household setting. But the dream would be to be able to shape real dough, which is, as we discussed earlier, way more malleable, elastic, sticky, and therefore tricky to deal with. But it would certainly be very cool to be able to manufacture pretzels of all different shapes, because then you can have your bartending robot bringing you beer while your bread making robot makes you a pretzel to accompany the beer, and then we can all retire. Okay, I want to thank the organizers for this opportunity to present in this beautiful city of Prague. And now I will hand the presentation off to Isabella, who will talk about other exciting and challenging problems in deformable manipulation.